idea. We're looking for the MZ here. This is just a sort signature to identify executables. We're looking for the MZ, but first we need to see a content type tag coming back, in the protocol saying, hey, I got application octet string. So there's, a little bit more likelihood that we're getting ready to see an executable, which is nice. Off the bat, we could look at this and say, well, it only applies to web, so at least we're getting web because web is most of the traffic, but we're clearly limited here. But the problem is that we want this type of detection, not because we want to know about every executable on the network. It's because we want to know about malware most of the time. I'm assuming for most of the people in this audience that applies. So when we want to know about malware on the network, well, that's not really commonly transferred with a lot of red flags going, hey, I'm malware right here. Your other technologies missed me, but here's a tag telling you this is what I am. A lot of times you'll see a client request, file.gif, and the server will come back and go, well, in this case, they requested file.js. So the server comes back and says, got your JavaScript for you right here. It's which I'm not an expert at JavaScript, but from what I know about it, I'm pretty sure it doesn't look a lot like that. All right, well, I've seen detection mechanisms out there looking for strings and things like that. Well, what about just trying to identify these strings? We'll actually talk about that in a bit more detail. I'm gonna skip over. Time check. 13 minutes. Okay. Right. We're gonna start running now. Okay, so what about MZ at the start of it? What if we just say, okay, forget what's up here. How about when the web traffic, the payload of the web traffic, or FTP or whatever, it starts with MZ? That's got to be a good starting point, right? Well, unfortunately, what we're starting to see a heck of a lot more of on the network, and this is kind of funny, on the network, files being transferred where even a lot of times right now, just the first 2 bytes are changed. And just changing the first 2 bytes will pretty much evade most every network-based binary detection product that I've seen to date, just from changing 2 bytes. And you go, well, of course, because it can't run on the host. You copy that file down, you try to load it, the Windows loader is going to look at that and go, yeah, no thanks, I don't know how to run that. Well, a lot of times these are transferred with some type of malicious JavaScript or Java type wrapper, which writes the file, and when it receives the file, it knows to just rewrite the first 2 bytes once it hits the disk, and then goes along its thing. So this is hilarious. I mean, the technologies that this evades would make your jaw hit the floor. Okay, we can't really look for the MZ starting there. And kind of going a little bit further down this path, well, what about even at the start of a protocol anyways? Something that I'm sure people in here have seen is, we've been coming across for a little while now, actually probably a couple of years now. EXEs embedded in some other type of transport that the malware on the receiving end knows how to receive properly. So this is a dump of that gift. This is something we actually found in the wild. Server says, hey, I'm sending you a gift. File starts as a gift. File's a valid gift. I put it in PowerPoint and we looked at it and it was pretty. But when we get far enough down, we actually see embedded inside the gift is an executable file that becomes extracted. And so now you think about this from a network perspective, right? This is why we have to treat all this data as just one giant array of bytes. And it's up to us to find some cool way to identify executables in there and then figure out if they're bad. Okay, so executable identification, the first part of the problem. We talked a bit about the magic number. This right here is the DOS header, which is the first structure of a PE file in a really cartoonish way. But the DOS header is made up of 31 individual fields. The very first one's magic number, next one is last page size, 27 other ones, which we'll look at in a minute. Next one's reserved, and then the last one is the offset to the PE header. Offset is just is what it says. It's an offset to where the next important header starts. So we can follow that offset. We'll hit the start of the P. It's actually the NT header. I mislabeled this. this here. But the start of the NT header, which does have the signature PE, hence my mislabeling. We have a 20-byte conf header and then an optional header, which is not optional at all. And I would love to know the history on why it's called optional. And the optional headers is actually, we can get a lot of interesting information out of there, which we'll look at. What's interesting is the start of that, if I go back a slide here, the start of that optional header, well, here's what we see. We see the start of that optional header. There's, I don't even remember how many fields are here offhand, 35, we'll say, it's in that neighborhood, very close to that. The start of the optional header starts with a magic number, which actually has one of 3 valid values. According to the specification, it has 4 valid values, but if you try to use the 4th one, I've actually never seen an operating system that'll run it, which is funny. But it has 3 valid values, 2 of which are the only 2 we really care about. So what's interesting about this is we can put all this information together and come up with a signature to identify PE files that is very, very simple to implement, computationally speaking, in terms of low impact on other processes or other functions that a process or product may be running. What I'm getting ready to show you assumes that we have the MZ fingerprint available to us. Of course, we looked at the example where we don't. There are ways around detecting with the same amount of accuracy when an executable is present that doesn't have the MZ fingerprint. Unfortunately, we have to skip it for this, but we can find ways of getting this information out more. So you can look at it there. All right, a pseudo example, basically covering what we saw in pictures, is if we find MZ, we can shift 59 bytes forward, read, it's a D word, so we'll just read in this offset. Read the offset, then we'll shift to whatever offset is given there from the start of MZ, do a test. Do we find PE there? Because remember I was talking about NT header starts with PE. If so, the conf header is 20 bytes, so we're going to skip over that, and we're going to look for one of our 2 bytes there that we're interested in. So all total, at least at a high level, because the logic for this is 3 pattern matches and 3 byte shifts, which is a minuscule amount of work. Half the crappy IDS signatures out there do far more work than this. So very, very high performance way of at least identifying the executable. Chance of false positives using simple statistics of this is 1 in every 32 terabytes of data, so definitely a lot more acceptable. And in reality, the chance of false positives is even a lot lower than that, because network traffic is not random. We assume it is to make the problem a little bit harder to solve, but statistically speaking, it's not. It's well structured. Even images to a great degree have some structure that we can see. So what we're looking at is structure, not random, which just helps the statistics there. All right, so implementing this. Okay, this is the only part where I'm going to talk a little bit about the product type stuff, and it's freeware. Otherwise, I wouldn't even be talking about this at all, or probably even this topic. Obviously, if you guys can't use it for free, then what good is it to you? There's a product, if you go to the NetWitness website, it's like download.netwitness.com, I'll put last slide, has it up there. You can get it for free. The logic implemented, there's these things called flex parsers or parsers, which you could think of as like signatures on steroids. Allow you to implement some kind of neat logic, which you see here. It makes a lot of sense, right? It's what we just saw. Find MZ, move forward 58 bytes. Yeah, that's right, because bytes. We're going to read in a 4-byte value, store it in PE header offset. It's a little Indian. We're going to move backwards, then forwards because we've moved backwards to the start of MZ and then forward to whatever value was given to us. And then we're going to find the value PE. That's where this logic stops. We could actually jump one more time. We can move forward another 23 bytes and look for 1 or 2 values if we wanted to as well, but that's it. All right, so cool. We're identifying executables. This is what you would see in the example that we looked at earlier in terms of, if you use the freeware. You'll see that the session, we have one session here, but it says, hey, the server is saying I got content type image gift. The extension that was requested by the client, was file.gif, but actually the forensic fingerprint of it is Windows executable inside that session. All right, 21.5 minutes. So how do we know if it's bad? Well, what's kind of neat is, as you saw even in the last example, is a lot of times just identifying there's a binary in a session is as far as you need to go. You know, of course, not all the time, but it's crazy how much stuff we find just by looking at sessions that have known executables in them, but the session, you know, isn't really advertising itself as having an executable. You know, say it's a gift or Java type file or JavaScript or whatever the case is. So that's kind of neat. But you know, what happens when we have less to go on? So what we can do is we can go. If you think back to the slide I had that showed the structure of the PE file with those umpteen different fields. Any parts of the PE file or the header that's fixed, and by that I mean if you're familiar with PE formats, there's some pretty recursive things that can happen in there in terms of offsets and trying to calculate relative offsets versus absolute offsets. But anything that's fixed and absolute in terms of the file, we can do analysis on, because that's the type of stuff that's going to be simple pipe comparisons and pipe shifting. And that actually leaves a lot. It's under 100 different points that we can look at, but it's approaching that neighborhood of a number in terms of thinking about a PE file and treating it just like we would any other network protocol. Think about talks or hear people talk about DNS anomalies and things like that. There's just a binary protocol that we can look for anomalies in. Okay, so first part of the PE file, first header structure, is the DOS header. The structure of it starts obviously with the magic number and ends down here 64 bytes later with a field called LFA and EW, which is, we saw the offset to the start of the PE header, right, or the ENT header. So the question immediately becomes, okay, that's the basic structure. What about the function of it, the function of the DOS header? As you can see, there's a lot of null bytes in there. And as you can guess from all those null bytes, the function of the DOS header is to look pretty. I don't know, it doesn't really have much of a function, as we'll see. It's a fairly obsolete header from a long time ago. Probably before most of us were born. Okay, so what does that mean? So we can look for, there's two ways we can take this analysis, just at this point anyways. There are certain values, there's about 4, and this knowledge came from fingerprinting what's normal output of normal compilers and linkers, and we looked at a lot of them, obviously Visual Studio, GCC, MASM, and kind of on down the line, Portland, etc. But what tends to be normal from them is we have some of these fields where we have non-null values, and there'll be one of a certain number of values or specific range, and the rest of these tend to be null. So we can take byte values that typically have a value and just check to see if they fall outside what's normal. Or we can look at the null bytes, we have a lot of them to go off of here, or look at the null fields and see if any of them are not null. And what's really funny is we could probably stop the presentation right now and you'd be absolutely, if you were to just implement this right here, you'd absolutely amazed like how much you find in terms of bad stuff just for looking for non-null bytes in the DOS header. It's almost goofy. So flex parse example of that logic, just to show you guys, it's not super advanced, all this stuff we're talking about. We're doing a single byte test, we're actually stepping through. So I just took a section of it, but for a single, testing a single field there, we're moving forward to actually a specific field, so we're moving forward 12 bytes, reading in a single byte in this case, storing it in num temp 2. If num temp 2 is not equal to 255, so FF, then we're going to set a flag, and that's it. And then later on, if that flag's set, we trigger an alert. That's it. So simple. What type of stuff do you find when you look for stuff like this? You find some crazy things sometimes. So here we see a lot of non-null bytes where there typically is. I'm not stepping through every field, obviously, for the sake of time. But we have our magic number, the end of the DOS header, E, LFA, and EW, and what's the DOS header function of the DOS header right now? Storage of import module string names. Okay, so the LFA and EW, actually, you can do a lot of tests just reading this single value right here. So a lot of people, anyone who's done any sort of binary analysis of PE files, whether it's network or host space, has obviously seen them in hex editors. You're obviously accustomed to seeing, a lot of people recognize this string right here. It's part of the DOS bootloader from the olden days when people even knew what DOS was. Is anybody here running DOS 6.1? It's awesome. Doom. Anyways, all right. So if you tried to load this obviously modern file in DOS, it's not going to work. Actually, I don't even know if DOS works anymore. All right. Yeah. So the reason we have this offset here is so that we can jump over the DOS bootloader when we're not in DOS, when we're in any normal Windows-based operating system. We hit the start of the NT header, and the loader, the Windows PE loader, continues to put it into memory, or parse it and put it into memory. NT signature, stuff in the middle. Got it. Well, what kinds of things can you detect, just by looking at that single value? I realize this would actually be a more interesting example if I picked something different, because there's so many different things that abuse this. Well, first of all, this looks a little different, right? What happened to the DOS loader in this example? Well, because nobody's using DOS, and the light was in my eyes, so I don't know if really nobody in here is using DOS. I'm just going to go out on a limb and assume so. Detection for it, because we're at 28 minutes and 59 seconds, there's detection. All right, so what we saw then in that previous example was this. I kind of edited this structure diagram. So we had LFA and E new just pointed to the very next byte, and the header just started there and continued on. Okay, great. Well, boy, wouldn't it be interesting? So that's where the offset is going to be the offset of LFA and EW plus 1, right? What if the offset is earlier? Can you do that? Can you detect that? What if the NT header actually starts inside the PE header, and is that even possible? Certainly would shave some size off of the file, at least a few bytes, and most certainly actually negatively affects the way some basic reverse engineering tools work, or at least binary analysis tools work. And as it turns out, as we see here, I need to move the arrow because the first arrow is covering the actual start of the cough header. We see that we're pointing backwards now into the DOS header. So the NT header is starting inside there and continues on. This is actually very funny to see. So because LFA and EW now is serving two purposes. One is an offset, so the loader knows where the next header starts. There also happens to be a collision that can be taken advantage of in this particular case, where we get a valid value for that OC. All right, so we'll move on. So there, we basically, in a single header, in the DOS header, presented 31 plus about 4 different deviations from normal, in terms of normal compiler, normal linker output, that we can look for through simple, just byte test, byte comparisons. Moving on, we got the next 20 bytes, which is the cough header. Unfortunately, we can't, at least right now, exploit every field of the DOS header to find those types of anomalies very easily. But 2 big interesting ones, if you notice we're looking at Notepad here. Number of sections, which I won't get into sections, but a normal number is in the range of about 4 to up to 8. Of course, it goes much higher and lower. But that's the normal range, and sections in the binary contain basically the code and things like that the programmer actually wrote, as well as other things. Then there's also the time date stamp, which is when the file is compiled and linked. And we can get that in there. So things that we tend to see in malware, first of all, is number of sections. 2, huge red flag, especially on the network. On the host, you can't get away with this so much. When you see this on the network, definitely a huge red flag. Why would you have 2 sections? Because you have a packer that's created this this new binary that's supposed to be a lot harder to reverse engineer. So they basically took all the code from the old binary, jam it into an encrypted section, and now the other section's just used as a decryptor to at least start the logic of decrypting. So they need 2 sections. This is not normal, especially on the network. And then the next one, of course, stands out. Date timestamp of 0. We actually have seen, by doing date timestamp analysis and things like that, we've actually seen funny things in there, like date timestamps, way in the future and far behind that we can also look for. All right, so that's the, this is awesome. We're at 32 minutes, 57 seconds. I chopped out a ridiculous number of slides, like probably 10, 15 minutes before this started, and we're getting there, almost to the end. Okay, so the optional header is enormous, which is where I chopped out all the slides, obviously. But to try to summarize, the optional header is actually very cool, because when we've gone through this exercise of fingerprinting what's normal from normal linkers, this is where we're basically at the point where we can look at a binary and say, oh, this came from this compiler and linker, because of the way certain values appear here. You can compare values to each other. Of course, you have major linker version, major minor version, which sometimes is a huge clue, but there's actually a lot of collision there between totally different linkers that create files totally differently. So through these other regions, we can do the same simple pipe tests, just shifting, because all these things are fixed values, fixed sizes. We know we can just read this byte, move forward, read this byte, move forward. D word, get it, great. We know we can calculate how far we need to jump down here. So all this stuff, very high performance. And how that translates is that when we implement this, just this type of stuff into like the flex parser, parser that I was showing you earlier, in real time, we can take, now in this particular sample set I took just to put these screenshots up here, there were 50,000 network sessions, and we immediately know, okay, well, of those 50,000, 473 of them have executables inside. Legitimate or not, there's an executable inside of there. And we find that out using the fingerprinting method we talked about earlier. Well now, so we could take this 2 ways, right? One is sort of ignoring that the statistical sort of detection of what's normal versus not. We could just say, all right, so of all our sessions that have executables, which of those sessions do we not find an extension of any type, whether a client requested a file name or a server sent it, or the protocol told us the name of the file, or whatever the case is. If the file extension is not exe or DLL or something like that, what's left? And so we have 75 of those sessions, in this case 4 of which are files that are named .text, and I put a lot of money on the fact that almost all 4 of those are going to be malware. Same with a lot of these low numbers, obviously not MSI, JS, yeah, that's probably malware, and the PHP ones that probably have some embedded interesting things in there too. Then we can also go the other way, and I just kind of skipped over all this and tried to summarize it by saying, all right, if we take the 473 sessions that definitely have executables, how many of them have these different attributes? Because this is also summarized in scores, but I thought this is more sexy to see like it broken out. But how many of these executables have, and Insidious, of course, when I went back into the office and showed them this cool stuff, they're like, yeah, we're never putting a product out that uses the word Insidious. I was like, you guys suck. Anyways, here's where we see each of those checks come up. We have 21 binaries with less than 3 sections, code size 0, on down the line. So each one of those tests we can pivot on, we can correlate to, we can find binaries that have multiples of that or not. All right, so I totally lied to Leonardo, it's 3648. But here's my contact information. If you download the freeware version of it, the current package doesn't have this parser inside of it that I've been talking about. Email it to me, I'll send it to you. Just make sure the subject line is obvious so I don't like delete it or ignore it. Or you could just wait like a month or two and the next major release that comes out on the web is going to have all this stuff packaged in. And that's it. Done.